Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
All right.
I was being crazy. I wanted to be a little crazy there for a bit.
Today's meme is a little crazy one.
It is. It's like, wait, is that the wrong arm? And
yeah, that's right. That's the right arm. So it's in the right direction. Chi-squared.
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 It's one of my main irritation points. I hate chi-squared.
But it's also not an insignificant statistic that people can use.
It's not insignificant, but it also insignificant. It significantly irritates me
for just this very reason.
It's exactly right. It's like, it's just, I'm getting into this to my irritation point of this, but it's just like, I hate when people are like, well, my software says chi-squared is 0.01 and yours says it's 0.07. It's like, I don't care. That doesn't matter.
But the fit doesn't look good either way.
Right. Or the fit looks terrible, but my chi-squared is low. It's great.
It's great.
Like, it's like people severely like overestimate how relevant it is and also don't use it properly.
Yeah.
I think it just annoys me. But you have to have it in your software. So it's like, if I told my colleagues like, hey, you should remove that from our impedance analysis.
Oh yeah. Well,
I might get
definitely necessary.
Overruled. It's not gonna fly. You need to have chi-squared. But it makes me feel like this lady. She's mad. She's just
very bad.
Yes.
Actually, on a slightly separate note, but related, Mark Orzum, kind of the father of I consider him one of the great, promoters of he didn't develop electrochemical impedance spectroscopy, but he did write the book on textbook. And he is retiring, in the process of retiring.
I think he said August. Is that what his
August? Yeah.
I might be off on the date, but I think he mentioned that he's going until so a few more months.
He announced his retirement, but he actually gave like a little 3-part webinar series that's on YouTube that let's see, it's associated with a channel that I don't have.
It's like neuro something. I saw it too. I don't have it off the. I could.
Yeah, I'm just. It's like, let me just go to YouTube and then find.
As well promote it. It's good.
Yeah, might as well promote it. I think it's good stuff.
NeuroNexus Technologies.
NeuroNexus Technologies.
So I think it looks like he's just sort of. I'm not sure if he's done the webinar version because Mark has always, to the best of my memory, I suppose, which is about 15 minutes worth of time, has done the impedance course at electrochemical society meetings.
Yeah.
So the electrochemical society, which is it's an international, but it's based here in the U.S. So for those who are in the United States, they have meetings in international locations as well, but it's sort of based in the United States anyway. Mark Orzum has done a impedance, I guess call it a short course, maybe is the official terminology. Yeah. So he's done that in most ECS meetings, to the best of my knowledge. And I mean, he wrote the textbook. He's published 5 quadrillion papers on impedance, and he's a really brilliant guy. And he's also a very nice guy.
Yeah, he's also very nice.
Met him once or twice, and he's exceedingly kind. He's very unassuming. He's a very humble guy. He's absolutely brilliant. So for what it's worth, our congratulations to Mark, and appreciation for everything he's done over his career. He'll be missed, but I hope he enjoys a very relaxing and
Well-deserved.
Well-deserved.
Retirement.
Yeah, non-oscillating retirement. I hope his retirement is not as
Is in a steady state.
is in a steady state and
Steady
not
state.
constantly alternating between happiness. There's your impedance
Yeah.
joke for the day. It's just terrible.
Yeah, it's that his retirement's very stable.
That's right.
It's a linear. It's
I hope
linear.
that Kramer's Kronig says that his retirement is valid.
Yes.
I hope the chi-squared of his retirement is exactly 0.
Exactly 0.
That's right. It fits. The retirement fits perfectly. Man.
That's good.
that's-
Oh,
I enjoyed that. Those are some excellent impedance dad jokes. I hope that if Mark
Dad
Orzum ever sees this,
Yeah.
he greatly appreciates the effort to which we bring these puns into our live stream. And with that, we can actually
Yes.
start answering your questions, because I know that there's a few of them.
Yeah, I
here.
got
So,
a couple questions that came up. So.
This one came a little bit ago, I suppose, just before we went live. So from Musa Budin, says, hello, I'm a PhD student working on the detection of aminoglycosides, antibiotics, by screen printed graphene electrode modified with carbon soot. Well, that's interesting. It's like graphite, carbon modified with carbon. That's strange, but interesting. The problem is I'm not getting any peaks. You should try getting peaks. that would be my advice. This is one of these questions that frankly is difficult to answer, because we don't have any other details about your system.
Yeah.
Just, as all we can sort of do is talk very broadly about electrochemical phenomena, which is that if a peak is an indication of a Faradaic process, right? So for instance, something like carbon, glassy carbon, different forms of carbon are obviously they are electrically conducting. They can work as electrocatalysts. But carbon is often used as a substrate for other catalysts for a good reason, because carbon itself does not always catalyze everything or catalyze everything well. So one of the reasons you might not be getting a peak is because graphene and carbon soot is just not a good electrode for whatever you're trying to do, whatever Faradaic process, redox process you're trying to do, which I guess is the detection of aminoglycosides, antibiotics. So I presume you're trying to oxidize or reduce it directly, or oxidize or reduce some byproduct. Something obviously must be electrocatalytic, electrochemically active of some sort, right? So you could try to expand your potential window. Very often carbon, for instance, something like oxygen evolution reaction or oxygen reduction reaction or hydrogen evolution, carbon, like a glassy carbon electrode will do those reactions, but not until you have a really high overpotential, because it's just terrible. It's just a really bad catalyst, but it will do it, but slowly and poorly. So it's like you see, like, oh, I'm not getting any oxygen evolution. It's like push your potential window by 200 millivolts and you'll start to see it. And it's like you might get a peak if you just move your potential, like you might be assuming, it should happen at this potential. And it's like, well, if you just give it more over potential, maybe you'll see a peak, because carbon might not be the best. So that's just kind of a general observation that can sometimes be the case, and especially with carbon. I don't know if you have anything else to add.
Yeah, because I'm actually I don't know what a aminoglycoside is. I was just looking up its chemical structure.
Me neither.
And
No clue.
And one thing I'd mention is that often, it looks like you want to do this on like a screen printed electrode as like a biosensor, right? Oftentimes biosensors, even like a glucose sensor, for example, like for detecting your blood glucose level, you're not usually detecting glucose directly. You're always detecting either something else that is electrochemically active. So sometimes it's like a glucose oxidase, or often it's the case that a glucose sensor will use an enzyme that converts the glucose into peroxide, and peroxide is the thing that's actually electrochemically active. So I would look at some of the, if you're putting, just as Neil said, if you're putting carbon on carbon, it's like, well, that might not, it's not really going to be an electrochemical reaction that's occurring. But oftentimes, if you've read papers where people are using these aminoglycoside for antibiotics, and they're using screen printed electrodes, they're probably using like a modified type of screen printed electrode that either has like an aptamer or some kind of reactive polymer film that is unique for sensing the amino glycoside. I think it's glycoside.
You got me.
And so, there's a lot of different like techniques that people use, whether it's aptamer chemistry. I've actually been learning about imprinted polymers. So like you imprint the aminoglycoside into a polymer, it's removed, and then when the biosensor is exposed to it, you end up getting a different redox reaction or even an impedance change. So I'd look at the papers that have demonstrated this, but it may be the case that the aminoglycoside by itself is not electrochemically active, but that doesn't mean that it cannot be used in an electrochemically based biosensor. So let us know if you have any further questions about that, or if you want us to elaborate. But generally speaking, the last thing I'll mention is that if you're doing a technique like cyclic voltammetry and you want to go to more sensitivity because you think that you can see it, there are techniques like square wave or differential pulse voltammetry. Those techniques are very, very sensitive and good at removing background current. So if you only were getting a little bit of signal and it's getting blocked off by the CV because you have huge background signal, then a technique like differential pulse or square wave voltammetry can be used. So those are the kind of the basic things I would mention based on what you've said in the statement here.
Very good. So next, Nathan F. Duran says, "Hi guys, always a pleasure to join your live stream." Well, there's no need to lie. I use CV using several scan rates within a voltage window, but how to know what scan rate is better for finding reduction potential? So I think there's a couple of things that I would propose. That's not what I wanted. That might help answer this. One of them is the speed of your reaction. The other is the double layer. So I'm going to simulate something for you and just kind of show you some ways that the scan rate would matter. So here we have in our software, you can see, let me make sure that it's sharing properly. It is. No, it's not. It looks weird. Why is it doing There we go. Wait, that's the one. Okay.
That's good.
Oh,
nope. Wait, did it change it back?
I did it twice because I'm very good at using this software.
Also
okay.
hide this. So
yes. All right. Perfect. I had us maximize, so I think it was doing wonky stuff. Anyway. Okay. So what I've done is I've just added a simple 1 electron transfer process, right? Mm-hmm. And you can see it has a very fast scan rate. Excuse me. Rate constant. Thank you. That's the word I was looking for. And let's just do 10 millivolts per second. And what I've done here is I've just added a few things. I've added a little bit of uncompensated resistance and a little bit of double layer capacitance. Normally, when you start the simulation, the double layer you don't add it, it's 0. So which isn't true in reality, of course, but if your double layer is non-existent, it doesn't matter how fast you scan for the first thing that I'm going to mention. So for a very fast reaction, almost impossible that your scan rate will affect, for example, the peak splitting, like to find your peak if the reaction's so fast. But what will happen is that if you have a substantial surface area or double layer capacitance, as you sweep faster, what you see here is where you can get to a situation where the peaks become obscured because of how thick the gap is between the positive and negative scans. So this is just one thing that can lead you to say, this is like 10 volts per second, but hopefully you get the idea. If I scan faster and faster, one of the things that can happen is also you're starting to see the effect of the uncompensated resistance a little more. The peaks are it just starts to go away. You don't even really observe them so much if I scan fast enough. And that's just the double layer band effectively is just dominating this this plot. So that's one thing to think about as far as like, well, if I scan really fast, what might happen? Now, the other is that if the rate constant is like really small, I'm going to try to make it exaggeratingly small, I guess. And this is, again, if you're looking for a peak, and now I'm contending with double layer as well. Here, what you can see is as I decrease the scan rate, I'm pulling the peaks back together and I'm reducing the double layer gap, I guess you could say, that the difference between the positive and negative scans. So here, this looks kind of normal, and this is because I've slowed the scan rate way down. Of course, the downside to this is it takes forever. So some of these are just examples to kind of talk through. For instance, you're saying, well, I'm looking for a reduction peak. It's like, well, two of the main things to consider are the speed of a reaction. Now, this is like exceedingly slow. This is probably not reasonable for most reactions. They're not this slow, but I'm just using it as an extreme example so you can kind of get the idea, right? If your reaction is kinetically slow and you scan very, very fast, you might like miss the peak altogether, and then the double layer also kicks in this case. The reversibility becomes more pronounced, I guess you say. The irreversibility, excuse me. Not irreversibility. The speed, the kinetics shows itself with the peak splitting more. Okay, but again, if the kinetics are fast on your reaction, then the double layer really kind of plays a heavy role as you start to scan faster and faster. And then if your uncompensated resistance is quite high, you'll start to see some of this kind of distortion as well as the current gets larger. And so if I scan slower, I can minimize some of those things as well, because the faster I scan, the more current I get. The more current I get, the bigger the IR drop. So there's like a lot of interconnected things here. To be honest, I'm kind of talking through all of them just to give you some idea, some concept, and hopefully showing you with these simulation how you can kind of observe those things. And then if you had a license for this, you could like try to match your data, for instance, with what you're simulating and say, oh, this is, I know about, you might know, for instance, what you could measure uncompensated resistance pretty easily. You might be able to know the double layer capacitance, for instance. It's typically about there's a number, it's like 0.1 farad per square meter, something like that. The number can vary, but if you know the surface area of your electrode, you could estimate what the double layer capacitance roughly is, and you could simulate this and see what you'd expect to see, for instance, for your peaks, depending on those parameters. So I don't know if you have anything to add. I just wanted to show how some of those things kind of worked.
Well, no, I think I was actually going to kind of build on what you said, because one of the next questions from LinkedIn from Joseph Wright was, how can your Aftermath platform help us quantitatively separate capacitive, pseudocapacitive, and diffusion-controlled contributions in CV data for heterogeneous carbon materials? And what Neil was showing, at least, was part of our simulation. It's not necessarily like what he was showing was for a homogeneous diffusion-controlled process, but you are able to show at least the capacitive and like the electron transfer Faradaic contributions. The way that we've programmed Aftermath in terms of simulation, purely from simulation, is really based on, you would say, kind of the Bard-Falknian way that we describe electron transfer, where pseudocapacitance is not actually really properly defined. But if you have a bunch of CVs and you're looking for pseudocapacitive behavior, oftentimes, like, it's not like we have a special like button that you can push that automatically looks through all the CVs and says, oh, this is diffusion controlled, and oh, this is capacitive. But simulation that accompanies your scan rate data for CVs of heterogeneous carbon materials can be used to show what's purely capacitive, what's Faradaic, and then you as the scientist would need to make decisions about what you would consider pseudo-capacitive. Again, a lot of this deals with, I believe it's the Bruce Dunn method, and using that, like, the scan rate raised to the alpha, where alpha can be a value between 0.5 and 1. And when it's 0.5, it's diffusion controlled, similar to the Randall-Sebstich equation. But if it's closer to 1, it's like linear. That's a normal like capacitive kind of thing. So, but our software, Aftermath software, has the ability to like find the peak, calculate the area. Like we have all those tools in our software, but I wouldn't say it's necessarily like special or designed for separating capacitive, pseudocapacitive, and diffusion control contributions in CV data. So Joseph, I hope that this was helpful, especially what Neil just showed you with how you can adjust some of these parameters and see the differences in the CV. Because I know when you deal with these more complex materials, you're not going to get an ideal looking perfect CV, but the simulation can be helpful, at least in that, right? Being able to determine what can be based on one thing versus another.
And just to clarify, I was looking up. I had it off by an order of magnitude. So again, if you're using this simulation or estimating things like the Helmholtz plane, the double layer capacitance, the typical value that people will use is 0.1 to 0.2 farads per square meter. That is the estimated capacitance of the Helmholtz plane, basically, which we call the electrical double layer. That was from my Mott-Schottky webinar, and I had in my head it was 1, and it's 0.1.
Oh, yeah.
So anyway, just when we're talking about estimating that, if for instance you are doing simulation and you want to put in that parameter where I showed you on our software, if you know the surface area of your electrode, you can multiply by 0.1 farads per square meter, and then you can estimate what the actual capacitance is if you can't measure it, for instance.
Yeah. So moving forward, we know we have a bunch of questions. We're going to go in the order that they have been received. If you do want us to answer your questions ahead of time and get priority, we do encourage you to go to our website and use the Contact Us form, create an account, and then put your question in, and we will get to it as soon as possible when the webinar starts. This also gives us time to like look at a graph, look at a chart that you may have, something along those lines. Are you going to share?
I was going to show it while
you're yeah. Just show.
So this is, for instance, you might have to. It keeps doing this thing. It's
like get one.
Yeah, I don't. Anyway. Very fun. They screen things. Anyway, this is our website, right? pineresearch.com/contact. For now, you can put like a technical product support or applications. But if you want to, whatever it doesn't matter what category. If you just when you start typing your question, down here, you can just put like, live stream question. Those are words, I promise. Just type in your question if you have one, and then we'll give priority in the first hour of the live stream to those who have contacted us. And like we said, put in your name. You can create an account, and that way it'll be on your profile.
And it'll automatically just show up.
That's right.
You don't have to,
and we will give some priority to that. Exactly. So there you go.
Okay, so Rebecca has a question on LinkedIn. Thanks for joining us. First off, thanks for the Mark Orson webinar info. Definitely check that out. And the meme today was to her question, which is about publishing impedance data. Is there any point of publishing EIS data without fitting? Is that ever done? As you know, my system shows some instability at low frequency, and I can interpret as due to interactions that would make my system unstable. Can I publish the EIS data with fittings that exclude the low frequency data and still show the data, but note it was excluded in the fitting?
Yes, you can. I actually did that when I was in grad school as well. One of the things that I did, just to give you an example, was it's a different system than yours, Rebecca, for sure. But I had a bunch of data, changed some variable, changed the applied voltage, changed the temperature, whatever I did. And I got a bunch of different impedance spectra. And all I really wanted was like the semicircle width, because I was just studying how the charge transfer resistance changed as I cycled through potentials, something of that nature, right? And I also had some wonky stuff happen at the low frequencies. And I just didn't care. So I basically did a fit, sort of, but what I did was I just did a semicircle I mean, it's a fit, but not really a circuit fit. It was just a semicircle, like adjustment to see what like just the width algorithmically was of my repeatable semicircle and how it changed. And I just ignored whatever happened at low frequency. And one of my first publications has data like that. So yes, you can. It's perfectly justifiable. You might get a reviewer who comes back and says, well, why didn't you, what's the equivalent circuit, or why did you fit, or whatever. For one is when you write your paper, you say something to that nature, which is like, all of the data these portions of the data were excluded from my fit, because, you say this more elegantly, but you say like, it's irrelevant to what I'm trying to show. It doesn't matter. The other possibility is, again, this is not data modification, not data deletion or anything like that. It's not anything unethical. But if you did, 100 kilohertz down to 0.1 hertz, and you're not wanting to fit anything below like 10 hertz, don't show it. You don't have to show those data. Like, just say you did impedance down to 10 hertz, which is true, and neglect to show the if the low frequency data just doesn't help show what you're trying to illustrate, just don't show it, because all it does is invite reviewer questions. And then you're forced to write your response to say like, that's an excellent point by the reviewer. They're very astute, and they should be the head of every publication in the world. However, I respectfully choose not to. Like, you have to go through that kind of exercise if you show the data. So do yourself a favor and either not show it, or very firmly, explain that you're analyzing the data that's germane to the point that you're making. And yeah, I mean, or chuck the full plots into your supplemental file, because nobody reviews the supplemental data. It's fine. That's the place for you to just use as the trash can of all the data that you collected. It's there. If someone wants to look through it, it's there. You're being thorough, but you don't have to like have it in the proper publication per se. So in short, the answer is yes. In long, it's all that stuff I just said.
Yeah.
I hope that answers your question.
She does have a, I guess a quick follow-up that we can get to. I'm interested in the change in impedance between surfaces at points where the data is stable and KK is valid, but I do think the low frequency data is interesting, and I do want to show it.
Okay.
Interesting.
So
okay.
Be careful about that. Don't get fixated on something you think is interesting. If you can explain it scientifically, if you're prepared to provide explanation, that's fine. But if your Kramer's Kronig, for instance, does not demonstrate that it's valid, you might be getting yourself in trouble. So be cautious, because you might think it's interesting. You might think that it helps you tell a story. But if the validity of the data itself is in question, that story you're telling might be incorrect, or at the very least misguided. So give it some thought and be sure that that's what you want to do. I think that's my advice.
Yeah, I know Rebecca has thought a lot about this. She, I think she's already published a bunch of papers so far. It's just kind of like, she's really thinking a lot about the system.
Sometimes less is more, especially as you get to the end of your PhD, as you get, kind of skilled at the publication game. Sometimes you don't need to say all the things. Try to, make sure you're focused in the message that you're saying. As we start, we want to kind of say everything. We want to cover all our bases. And a lot of times I'm not saying this is your case, because it might be perfectly reasonable in context to make those kinds of analyses or whatever. And I know what this feels like is you have all this data, you understand it better than any other person in the whole world. Obviously it's your data, it's your system. But you get fixated on wanting to tell all the stories. And it's like, sometimes you need to reel it in, tell the primary story that you need to, and don't open up a can of worms. Because everything you put on a slide in a presentation for your thesis, in a conference presentation, everything you type into your publication, that opens up a question. It's fair game. Everything you show is fair game. So if you don't want to open up a lot of questions to which you frankly may not know the answers, don't open that door.
Yeah.
All right.
Okay, next question. Hi, I am a PhD student from Morocco. We have a potentiostat in our laboratory, and I want to begin the work on lithium-ion batteries and sodium-ion batteries. Can you give me some advice to begin?
Oh boy.
Yeah, it's like starting things up.
Buy a glove box.
Buy a glove box.
You're gonna need a glove box, my friend, if you're gonna make these. I assume you want to make batteries.
Yeah. I
Um,
guess.
Advice where to begin. I wish someone had given me advice where to begin when I was starting.
I guess that's why. That's
why
why they're asking.
I know. Let me think about this. Like
It may also be hard to tell exactly like where you're starting. It's like, okay, you are a student in
Mhm.
Morocco, and it's like, is your lab established doing this kind of stuff already, and you're just a new student, or is the lab established doing other things, and you're trying to branch out into the field of
Yeah,
lithium-ion batteries? Like you just said, you have a potentiostat in the lab.
that's a good step.
That's a
but
good step.
all of the experimental stuff will require some some effort. So, I mean, the first and most obvious thing is read a lot of papers. If you're very new to batteries, I will say, as you start reading some of these papers and looking at publications and stuff, um, it might be like you don't know what you're looking at. It's confusing. That's okay, right? To a certain extent, one of the things about battery research specifically, which is it's unique to batteries, but it's not unique in a general sense, is that it has its own terminology, its own um, kinds of plots, charge discharge plots, and capacity plots, and these kinds of things. Um, just read enough papers initially to get yourself, if nothing else, like used to seeing the kinds of things that people publish in battery papers and that people show for battery data. So that'll be at least a step. You'll be like, well, okay, I've seen these charge discharge curves. At least I'm used to what that shape looks like. So when you start doing real experiments yourself, you might know kind of what to look for. That's one, pattern recognition is something that's very human,
Mhm.
generally speaking. In science and research, it's very powerful, pattern recognition.
Oh,
And
yeah.
so, I mean, obviously that's like the basis of every research project, basically, is you start from something that someone else has done, something that's well known, a system that's repeatable and reproducible, and then you branch out into your own ideas and research and so forth. But recognizing the patterns of how those things are is a really valuable kind of a thing. Beyond that, honestly, there's just so much. I mean, I could talk for hours, and I don't know how valuable that would be, especially to everyone else who's just staring.
Yeah.
Um,
With their own questions.
yeah. So maybe, Saeed, I think if you have like a specific question, like maybe like one aspect that you want to know, like I can explain how C rate is calculated. I can explain how capacity is calculated. I can explain what happens during a charge or discharge. Like I can explain all these things, but I just don't want to drone on forever here. So if you have a specific question about batteries that you want me to try to answer now, I'm happy to do so. But without that specificity here, we're gonna move on. Again, just in the interest of time, I could literally talk for the next like 3 hours and just talk about batteries forever, and it's a lot. So
I'll also say, just without selling anything, because we don't offer it, but there are lots and lots of battery courses.
Mhm.
Period. Just like the Electrochemical Society has a battery short course, completely virtual. And I know that there are lots of just like if you're really starting and all you have is a potentiostat and you have no battery experience at all, then there are courses. There's like full on, not like school courses, but like workshop related things, virtual courses. There's a ton of them that just exist. So I would check those out as well if you're like starting from scratch.
And if you're looking for free content as well, because a lot of those they do cost
Oh yeah,
money.
they cost money.
YouTube is a great reference as well. There's a lot of videos on YouTube, just generally speaking, about batteries, about how this or that
Yeah.
works. For us, because you came to our live stream.
Yeah.
We actually don't have a lot of like specific to battery videos, I think, at this
Mhm.
point. But this live stream, this is episode
'Cause I
130
haven't
something, I
made
guess.
it yet.
I know we haven't made it yet.
We've been so busy.
It will happen
It will happen.
sometime in the next 70 years, I promise.
Yeah.
When batteries have been replaced by some other incredible energy source. But this live stream specifically, I have talked about batteries many, many times. So for instance, if you're on our YouTube channel and you like search for batteries or battery or something like that, you will probably get a ton of results. Why don't I
Oh.
think I think I could do this. I'm gonna see if this works. Actually, I'm just
Uh-huh.
curious. It's like if I search for batteries on our YouTube channel, what happens? Well, you get pitch meeting stuff, which is just silly. But so okay, yeah. So here's an example, right? Just one way that we can help you ourselves, because don't let it ever be said we
you
don't
need
provide.
to watch the research pitch meeting
I
that you
know.
did.
Watch
That's
the research.
gonna help you the most.
For sure. It's
Right
like
there.
it's everything that's gonna help you. Where is the thing here? There it is. So for example, I just went to our website, excuse me, our YouTube channel, which is you're probably on right now if you're watching this. And there's a search thing here at the right? And I just typed in batteries, and you can see there's some silly vids. There's also episode 7. We have a podcast. We have a cyclic voltammetry video. We have a playlist. We have all these different episodes of our live stream. We've done again 130 some odd at this point. So you can see this one I talked about pit and git. There's batteries in this one. I mean, the list is actually ridiculously long. So and there's timestamps. So if you click on episode 116 or whatever, there's a timestamp in there for batteries somewhere. So you don't have to just watch 2 hours. I mean, unless you really like us or something, which something's wrong with you. But well, anyway, please feel free to browse our YouTube channel. You'll find a lot of battery stuff there. Might be helpful. You might. I know at more than one occasion I've shown the calculation for C rate. I've shown how to do how pit and get work. I've shown how discharge works. I've shown how uncompensated IR drop manifests itself. Like I've done all of these things over the course of this live stream. So hopefully that'll be a resource for you as well. And like I said, you don't have to apologize for confusion. That's what I'm here for. That's what we're here for. So if you have a specific question, you just want to know one thing, you can't learn all the things at once, but you can learn one thing at a time. Compartmentalize it. If you're just thinking today, I just want to figure out how does a galvanostatic charge discharge work? Or what happens when I'm charging? What is an anode? I mean, all these are simple questions, but if you haven't done it yet, you don't know. So if you have a simple question about any of these things, let me know. I'll try to answer it for you now or during any of our live streams. So hopefully that kind of helps you out there.
Yeah. Kind of moving on to questions. Thank you for your answer. To be specific, it's streptomycin. In the literature, screen printed carbon electrode has been modified with multi-walled carbon nanotubes. And then moreover, I have done preliminary characterization with ferrocyanide using CV and EIS observation, IP enhanced, peak separation reduced, and RCT of bare electrodes significantly reduced. Well,
modified electrode, he said. He clarified. I think the last thing he meant modified.
Modified.
So the RCT was better with the modified. That makes sense.
Oh, right. Yeah. The RCT was better, right, from the modified versus so
but again, that's for ferrocyanide.
Yeah, a redox active molecule.
Right. Which is everything does ferrocyanide. Like you could put your finger in there and connect it to your potentiostat and it will zap ferrocyanide very happily, right? Don't do that.
Don't do that.
Please don't do that.
Yeah.
I'm kidding. My point is everything does that reaction. So
pretty well.
For sure, you have modified your electrode and very likely you have improved its electrocatalytic activity. But fundamentally, it's still carbon. And if carbon doesn't catalyze well, whatever the streptomycin, whatever it is, then you might have the most active catalyst ever that still doesn't catalyze this specific reaction well.
Yeah.
Right?
Yeah, that's right. That's right. Ferrocyanide works very well on carbon. At least you know that it's conductive. You know that your electrode's conductive, but the streptomycin is maybe not conductive. It's unable to do a redox reaction, and so you may have to do something else, possibly. So hopefully that's helpful.
Yes.
Okay, all right.
There was a question in between there that's right up your
my alley.
your alley, because you understand how potentiostats sort of work.
Sort of work.
And
Okay.
Clint Robbie says, can you explain the flow of electrons and currents in a 3-electrode system?
Yeah. I mean, the flow of electrons is that, well, I guess maybe there's further clarification. So the flow of electrons always is between the counter and the working electrode. And so I guess we'll use I guess I'll share my screen and just.
Flow of electrons and current is redundant, by the way.
Yeah, it's a little redundant. You could say the flow of ions or something like that.
Yeah.
But I guess, this is a relatively simple question. I don't know if we need to get into how the potentiostat works, but if you have your 3-electrode cell and you have, say, a working electrode that's like glassy carbon or something like that. So you have working, and then you have, say, reference. And the reference goes in, and that usually has some kind of like frit here at the bottom. And then there's some kind of wire, maybe silver wire with some silver chloride in it. And then you have your counter electrode, which is often like a coiled platinum wire. So this is your counter electrode. So the flow of electrons, and these are all connected to your potentiostat. The flow of current is between the counter and working electrode. That's where the flow of, well, it's ions or current. So you have ionic flow that moves between them. So the electrons, and it depends on what you're doing. Like if you're doing a reduction, but like electrons could be moving, if you're doing like a reduction, they could be going from the working electrode to ions in solution. But then electrons from the solution can be going into the counter electrode. So you're doing the oxidation at the counter electrode. And so this would be a reduction. And then here, conversely, there's an oxidation, and they flip if you're doing the opposite reduction or the opposite reaction, and you reverse the polarity of like the working and counter electrodes. So this is the flow in a 3-electrode system. You have current that flows between the working and the counter electrode, and that's it. I mean, if you want more clarification, I'm happy to do that, but that is where the current flows between, and the reference is just somewhere in between that. So there will be current that naturally passes between, counter and reference and working. That's where IR drop comes from. But the flow of current always is between the counter and the working electrode. So hopefully that's helpful. Very simple. Didn't need to get into
how a potentiostat works.
All right.
Well, that's good, because I don't know how a potentiostat works.
It's like, let's get into operational. It's like, no, he just wants to know where the current, where the electrons
pluses
go.
and minuses move.
Where the pluses and minuses move.
Exactly. It looks like too here for us, like somehow the comments like replicated themselves. So but that's why it looks longer than it is. But anyway, I think hopefully everyone's still got their questions here. We have a duplication somehow on our end on the Livestream. It looks like it.
Oh,
it looks like there's more than there are, but I don't know why I did that. Anyway, next question I think is here from Are My Comments Showing? Apparently they are, and they asked, "Hi, you want to make a calibration curve using CV?" Don't tell me what I want to do. You don't know me. Do you stir the solution while adding higher and higher concentration, or switch solutions containing a series of concentrations? The goal is to target concentrations at the limit of detection. All right, so there's a few things I'd say to this. One of them is if you're trying to find the absolute limit of detection for an electrode and some material, right? That would be sort of definitionally the lowest possible concentration for which you get a repeatable signal, whether that's a peak in your CV, which if you're doing CV, I guess, or whatever the current is that you're trying to obtain, or whatever it is, right? So the smallest concentration for which you can repeatedly get a signal, and under the best possible conditions, let's just say. right? So that in some cases that might mean stirring, because you're sort of in some, you know, it depends. It's tricky. Like if you're stirring, depends what the electrode is compared to where you're stirring. But let's just say, generally speaking, if the solution's being stirred, um, you're well mixing, you're producing some convection, and so possibly it will be more likely that you detect some, you know, small concentration of material than if you don't stir. So that's going to be like the absolute best possible way to get your lower limit of detection. Now, there's a couple of things I'll add to this, right? One is that if you, let's say you go to like, I don't know, 1 millimolar, right? And you stir the solution, you force convect, and you get a peak, or you get a signal or something, and it's like, oh, I've detected my analyte. But if I don't stir, I don't see anything. Like the diffusion, you know, layer or something is obscuring it. You don't really get any detection. And your device, you know, for which this is meant to be used in, does not include stirring of solution. Does this make sense? Right? Then you're testing the lower limit of detection under a condition for which your device is not using. So you can look at it as almost like two different kinds of limits of detection. One of them is like the best absolute one. So like stirring it, ideal temperature, ideal whatever. And then the other is like, okay, well, in a real world situation, if it's like I'm detecting, you know, some chemicals in like lake water or something, and I have like a test strip, and I'm just sort of, it's stationary, you know, drop of liquid. It's at whatever temperature it is outside. You know what I mean? Like you have whatever conditions you have. You don't have the ability to like put it into a vessel with a water jacket and a stir bar and all the things in your laboratory. So you might want to figure out, okay, well, I can detect 1 millimolar under ideal conditions, but like I can detect 5 millimolar when I don't stir or something like that. So that might be a better way to think about what your lower limit of detection is. The other thing that I'll mention as far as the calibration curve is adding higher and higher concentration. Sometimes you do the opposite. Sometimes you start with a high concentration, then you make serial dilutions and you go down, right? But ultimately, another hallmark, let's just say, of a like quality detectable electrode of some kind is that it needs to be like reversible and reproducible. And so, for instance, if you check high concentration to low concentration, or low concentration to high concentration, and then you do random concentrations, you should get the same calibration curve, right? If you do like low, higher, higher, and your peak height goes up, or you do the opposite and your peak height drops as you drop the concentration. If you do like 1, 7, 4, 10, 3, 9, you know, you go all over the place, you should fill in those gaps and it should be the same. That would be, because otherwise then you have a history kind of a thing, right? It's like if I start high and I go low, is there like adsorption going on? So I'm getting a false lower limit of detection. Like I only have 1 millimolar, but I have some that was hanging around from my last test on the electrode surface or something. And so it's making me think I have a detection, but I don't. You know what I mean? Those are some other things you want to do to get a quality calibration curve, is do different orders of your solution. So you're not always going to go higher concentrations, lower concentrations. You might want to mix it up. Start the solution, series of concentrations. So those are some of the thoughts I have about making calibration curve, about getting your limit of detection. I hope that kind of is helpful. Also, there's
some follow-ups.
Sure. Go ahead. Yeah. What do you have?
I mean, his follow-ups are just
sorry.
I'm wondering about the differences in the non-Faraday stuff when you're switching solutions and electrode positioning. He wants to know, what do people normally do?
So, for instance, if you're changing the concentration, one of the things that you probably want to make sure you do is keep the ionic strength the same. So, for instance, if you have like 1 molar is high, but whatever, let's just say 1 molar total concentration of your analyte, that's like super concentrated and you get a nice looking peak, right? Then you cut down to half molar of your stuff. Well, you're going to want to add half molar of a anything, a non-contributing whatever. So your ionic strength is the same, because then in theory, the non-Faradaic contributions will be the same. Carbon nanotube yarn microelectrodes. Okay, yeah. So this is this probably advice
No.
is fine for that.
Oh yeah.
But like keep the ionic strength the same. So for instance, when you go all the way down to 1 millimolar, you might have mostly like, let's just say like perchlorate or something non-adsorbing ion. You know, maybe like KNO3 or something that doesn't contribute to any Faradaic processes. That's not going to clog up your electrode. That's not going to cause any issue, but it's just a background electrolyte, whatever we call supporting electrolyte, right? Add enough of that so your ionic strength stays the same. So that would be a way for you to verify that the background current is roughly equivalent no matter what. And then the only thing you're changing is the concentration of your measurable analyte, right? And then electrode positioning, I mean, again, it's the same conversation as I made with respect to stirring or not stirring. What's the position of the electrode expected to be in the field device? Because I assume that's what this is meant to be. It's like in a device used in the field, so you can consider the lower limit of detection for what the orientation setup physically is for your electrodes when it's used for real. And then you can also make it as good as possible to try to push down your lower limit of detection. That might be like proof of concept, might be good for publication, might be good just to see how well it can perform under ideal situation. And that might be something like putting your reference and working electrodes as close together as possible, making sure the counter electrode is farther away, not interfering, just some of those kinds of things. So those are some of the ideas. And KCl is supporting electrolyte. You can be careful. Chloride can sometimes absorb and clog up active sites, maybe not with carbon, maybe you'll be okay. But chloride, salt water can also cause degradation of like metal components and things like that. So you might consider nitrate. Nitrate or sulfates are usually, I think, pretty benign. Careful with sulfate though, it's got a -2 charge. So your ionic strength, you got to like divide by 2. There's stuff like that, right? You want to make sure that like the total number of minus and plus is always about the same. KCl is easy because it's strong. Perfectly dissociates into K plus Cl minus. So it's like whatever the total amount of Cl minus or whatever the total amount of minus and plus you have is easy to supplement when you have something like KCl or KNO3 or whatever, right? So anyway, hopefully that kind of helps. Looks like seems to have understood. So
yeah.
So yeah, give that a try. Good luck on your calibration.
Yeah,
curves.
very good luck with that. All right. Moving on, I'm working with symmetric lithium cells with solid polymer electrolytes, pouch cells. And I'm trying to figure out how to get the potential that is present in the double layer. And is a potential gradient in the electrolyte ever present? I'm thinking electron neutrality means that there is no potential present.
I'm sure there is one.
What
There's a potential in the electrolyte.
In the electron? Yeah.
I mean, there must be.
Yeah. There's IR drop, between these. I've asked you this question before in the past, but it's like I've always been told like battery scientists never think about like the potential of the electrode in terms of the electrical double layer.
No.
Like, they never think about like, oh, the anode potential and the cathode potential are equivalent to the electrical double layer potentials. It's not like not a thing that they think about.
Like the double layer just doesn't exist for batteries. like physically, of course, there's always a double layer, but like it just doesn't like conceptually enter the equation very often because you have so many other things, I think, whose capacitance and energy storage capabilities far outstrip it. Which is to say the actual battery itself is a massive capacitor, and the SEI is also has capacitive properties and is much thicker than the double layer. And I think that just they all just kind of make the double layer like somewhat irrelevant, I guess. I don't know, like the double layer is so fast, right? And let me think.
So for like for comparison, when you measure a 3 electrode cell and you measure the working electrode potential, like glassy carbon, gold, whatever.
Yeah.
the potential of your glassy carbon electrode is the potential of the double layer. Like what you measure, and here's the picture. Let's just go to the
It's
picture.
that picture.
So the picture is so the picture is that if you have a it's not just a picture, it's I guess it's an equation sort of say, but like if I have a wait a minute.
Don't you have it?
I have a picture right here. I
Oh,
just have to
well,
get
that's
rid of this stuff. I already have an electrode system. I don't need to
I already drew it. You set
I
yourself up.
already drew most of this. I can only
The O must remain.
the O must remain. It's not allowing me to, it's only allowing me to erase. Here we go. Here we go. So it's reduction, then these oxidations. Thank you. Get rid of that. Get rid of that. Reduction. It's going away. Right. Okay. So the working electrode potential is just what you measure is working minus ref. That's the potential that your potentiostat will tell you, right? That's the potential. We'll call it E. This, and there's an IR drop component to it, but the potential of working is equal to what's known as the potential of your metal electrode. That's the carbon minus the solution potential, and this is like solution. And this is just the difference, if you will, between, it's like if you draw a picture of a working electrode here, you end up getting this kind of this gradient, this field, and it's like, okay, this is phi m, and this is phi s, and it's just this, and this is the double layer, like this area here, this huge potential drop, like out here in solution, ions don't feel any like difference. This drop between them is the potential of a double layer. So that is in a traditional 3 electrode configuration. Now this is, and I've described this to people, this is also like independent of a potentiostat. You just put a piece of like platinum wire in salt solution or something, that will naturally form. So these double layers will naturally form, and they will generate, and that will be the potential, if you will, of your system. So there's most of the time in these 3 electrode systems, not talking about symmetric, lithium cells, but the double layer that's formed between the difference between those two potentials is also equal to the potential of the Nernst equation that's based on the analyte in your system, like the concentration of your redox species. So those two things are all equal to each other. The potential based on the redox species that are in solution is equal to the potential of the double layer. And so as the double layer changes, because you're using the potentiostat to control the double layer, you're also simultaneously changing the ratio of your oxidized and redox species from the Nernst equation. So all those things are always normal in 3 electrode configurations. But battery people never think of it that way. They're always just like, the Nernst equation for a battery person thinking about an anode or a cathode is actually looking at the change in the Gibbs free energy, because carbon with more or less lithium intercalated into it has a different potential, and there's a different reaction, it's a different redox reaction than just the potential of a redox reaction homogeneous in solution, or the ratio of those two things. So
I'm trying to think about it in another way too, and I'm just trying to rationalize it in terms of like in my Mott-Schottky webinar, I talk about one of the reasons that Mott-Schottky works for a semiconductor is because the thickness of the space charge region is bigger than the thickness of the double layer, which means that it has a smaller capacitance, which means its impedance dominates. That's effectively it, right?
Yeah. And the potential is one number. It's just the
That's-
potential of the system
That's right.
is whatever, 1 volt, but it shows up as a different capacitance and a different impedance if the capacitance of those two sides, the inner Helmholtz plane versus the the depth of
Space charge.
the space charge region, are going to be different. But the charge neutrality, like they neutralize their charges by separating them
Yeah.
based on the potential, which is ideally just one number at any given point in time.
And so the battery is a little different because it's not one number. Is that the idea?
It's that
Like in terms of the layers, because from the battery's perspective, it's like
Mhm.
there's more going on. It's like I don't even know. I just think it's like
batteries are also much more complicated because they're not planar electrodes. They're like
Yeah.
they're porous. I
Yeah.
mean, I've even heard about people. Someone was telling me there are people who study double layers of pores that are on the same order of magnitude as the double layer in terms of its size. Like you can imagine you have a 1 nanometer pore and your double layer is 1 nanometer.
yeah.
What exactly does that look like electrostatically? So it ends up being like very complicated. But there are people who study that.
Yeah.
But yeah, I mean, double layers do exist. As you know, there's tons of interfaces as well. But yeah,
It's just like,
are they equal to each other?
well, and the situation is just far more confusing when you try to think about it through the lens of like a traditional electrochemistry setup, like the electrode thing with double layer or whatever. Because it's like the battery is concerned itself with it's a certain thickness of the anode to the cathode, the electrode, and it's like you said, it's a porous microstructure that's intercalating or deintercalating lithium or sodium or whatever. It's changing its composition. It's Gibbs free energy all the time. The surface condition is a lot of times reflected with the SCI, which is like a layer. It's not a capacitance. It's like a decomposition layer.
Yeah.
There's an interface there.
Mhm.
When you do impedance, for instance, you get semicircles, which means there's capacitive elements. There's capacitances associated with each like interface. It's just never really discussed as double, you know what I mean? It's never discussed as double layer. Like you'll get a semicircle corresponding to the SEI, and it's like, well, that's the capacitance of the interface with the SEI or something of that. And that's the charge transfer resistance of the SEI. And it's like, if it grows over time, it means the SEI is getting too thick and it's inhibiting in some ways, it's not helping or whatever. And then it's like the capacitance of the anode or the cathode is just its own charge storage mechanism. Like we don't talk about the double layer almost ever, you know what I mean? And I think it's because its capacitance is so much smaller than those that it's almost like you're adding a million to one, and then it's like, well, it's still a million, something like that. I don't know.
Yeah, and then the question is, well, the other thing is it's like, how does that? It's like the double layer is a capacitor and it has a voltage associated with it because it stores charge. Is that voltage equal to the voltage of the potential, sort of say, is it equal to the potential of the anode or the potential of the cathode? And I think that's a good question, and I don't actually know the answer. People, just as you said, people don't talk about it in that way.
It's not to say that no one has. There might be a paper or two that talks about it, but you won't find it very often. You won't even find double layer mentioned in a lot of battery papers. To my memory, anyway. I mean, I don't. Maybe it is, and I'm not like thinking about it, or perhaps, but it's just my memory or my hunch is that you don't really even see the double layer discussed at all in a battery. The average battery paper, they won't even talk about it. They won't even bring it up.
Yeah.
So, but I think as a general rule here, like when you have electrolyte, you can certainly have a potential gradient there. I know it's interesting to think about because you have a symmetric cell. So you might say to yourself, well, if my voltage is, but is exactly zero. Is there any gradient? I mean, and I guess in some technical sense, the net gradient is zero. You might have local gradients or whatever, but like
Sure.
if there's zero voltage, the net gradient, so to speak, between those 2 points must definitionally be zero. That doesn't mean there isn't a change in those layers locally or something like that,
Yeah,
right?
it's like,
It'll go up here, then it'll go down, and then it's net zero if it's 0 volts over
well,
over.
well, I always think about, when I think about these pictures of like, okay, yeah, maybe it's net zero. Also, I'm assuming in a symmetric cell, there is a voltage difference in a symmetric cell when you charge it and discharge it, right? So
I think so.
so naturally, when you do it, when you charge up your symmetric cell, even though it's both lithium, right, on
There are
both
different
sides,
amounts of intercalation or
there's just
something.
different amounts of
or
intercalation,
different surface states or something.
different surface states, but
yeah.
they create a potential difference between them. And I always think about potential differences as meaning that it takes energy to move from one potential to another, because that's what potential is. It's energy per coulomb,
Mhm.
right? And so if you have no potential difference, which is the case when you have, like, say, a pure conductor, a pure metal, it means that it takes no energy to move electrons from one place to another. But the moment there's a potential difference, it takes energy to move either up or down in relative potential from one thing to another. So so is there a potential gradient in the electrolyte? I think so. It's just and maybe that's what he's ultimately getting at, is understanding the nature of the electrolyte itself.
I mean, maybe another way to, I don't know if this is the right way to look at it, but it's
Mhm.
like, what's one of the hallmarks of a conductive metal, a conductor, right?
Mhm.
There's no potential gradient. There's no, right? That's
Yeah,
within a metal,
it's conductive. Yeah.
it's conductive. There is no gradient. There is no voltage difference. If you have a strip of copper, there is no voltage difference or whatever. Like that's
Yeah, it doesn't require energy for the electron to move from here to here.
right.
Maybe, of course, if you polarized it,
Sure.
and you do stuff like that. But if it's neutral, then
Right.
and it's a conductor,
And so an electrolyte is not that. I mean, it's
it's
concentrated, but it's not
it's not a pure conductor.
right.
It does take energy, and that's why.
So it must have a potential gradient. Sort of just by that
Yeah.
comparison, you might say, okay.
And electrolytes in batteries are also like the IR drop in a battery is extremely low, right? 'Cause you're talking about
Yes,
milliohms.
it only
Or-
no. So the IR drop can be significant. The
Mhm.
R
Oh, the
is
R.
low.
Sorry, the R
Yeah,
is low.
the R is very low in a battery. The IR drop can be high
be
because
high.
you're often working with high currents.
Very high currents. Yeah.
exactly.
Yeah. So in that case, because oftentimes, like, we'll draw solution resistance in those things as just a straight line from like one point to another, because it is in a way like kind of a linear drop off with resistance because of the IR contribution. But I feel like I don't know if that helps you at all. It's like I think we talked a little bit about it, and that it is complex, but
Yeah.
it's not like a traditional. That's the thing. Like, whenever I see pictures or images of like batteries when people are presenting, and they always shows like anode, cathode, electrolyte, separator. It's like that's not even remotely close to what it looks like physically. It's
Oh,
like
yeah.
everything is it's like smushed together.
That's the engineer's description. It's like, here's a thing, that's what it is. And
Yeah.
it's like physically it's more complex, chemically there's a lot going on, and we just
And then when you look
simplify
at like a double A battery, I always thought like, oh, there's an anode and a cathode, and it's like it's this big, but that's not what it looks like on the
stuff.
inside.
It's a big jelly roll.
It's a big jelly roll on the inside. Like those two electrodes are like wrapped around each other.
That's why it's a cylinder.
That's why it's a cylinder.
That's how you can get so much energy out of a tiny little cylinder, because it's like,
Yeah,
I don't know, it's like 100 layers or something.
Yeah,
It's
but when
rolled
I
up
was
super
when
tight.
I was a kid, I was just like, oh, anode and cathode are on these two sides, and there's so much space between them. These ions just magically move from one place to another.
There's a plus on one side and a negative on the other side. The electrons just move one way. That's it. They just go inside this tube. It's an empty
in
tube.
this tube. It goes here.
Or
Nope.
it's just filled with green paste and it just works magically. It's just a green paste, because if they ever leak, it's usually green.
Yeah.
Nickel.
Coin cells are perhaps the most representative of what a real battery like construction is.
Yeah,
It's
'cause
just like
it's
two
two layers
big
within.
area, flat, very little space in
I
between.
mean, that's kind of what a pouch cell is, but it's just a lot of layers.
That's like what every battery is. Every battery
Well,
is just
every battery is that. It's just
larger.
whether it's flat or
Or
it's wound into a cylinder.
yeah,
It's just a bunch of layers.
it's just a bunch
over
of
and over
layers.
again.
Batteries are just bunches of layers.
Yeah, yeah, exactly. Oh, so it looks like
Oh yeah.
yeah. So she said I was mixing SEI and double layer. I thought double layer means SEI is stable, and the capacitor from EIS was from double layer, not SEI. What? Yeah, again, I think it depends which EIS capacitor you're talking about. So again, the SEI usually manifests with its own semicircle in impedance, right? And so the semicircle in impedance you get associated with the SEI, in theory, gives you information about the SEI's resistance and capacitance. So those quantities associated with the SEI. But then there's capacitances and resistances associated with the anode and the cathode as well. And so there's an open question as far as what is that, right? You might consider that to be the double layer on the anode or the double layer on the cathode or something like that. Or it's the, like I said, maybe it's the capacitance of the cathode or the capacitance of the anode, which isn't really the double layer. It's like the microstructure. It's a bit, it's storage of lithium ions or something like that, right? This is a tricky discussion. Again, I would, neglecting the potential conversation for a moment, that's what I would anticipate. You like if you're studying a material, it's like an anode or whatever, and you get two semicircles, you might say the first semicircle is the SEI, and the second semicircle is the anode or the cathode, whatever you're studying, and that the capacitance of that main semicircle, let's just say the bigger one, right, is the charge storage capacitance, of the material you're studying. Because even if you want to acknowledge that there's a double layer, like I said, neglecting the potential conversation, the double layer is a charge storage mechanism, but the double layer is never going to store as much charge as the battery itself, or even the SEI with secondary storage mechanisms in the SEI. The double layer is almost certainly going to be a smaller capacitor than the battery itself.
Yeah.
So it's like, probably there's a series almost, right? You almost like add the capacitances together, and it's like you're adding a million plus like farads, for your battery or whatever, plus 1 farad for the double layer, and it's like, okay, well, it's contributing, but it's not doing anything, right? It's like when it's like if you have a 2-year-old and you tell them to clean the house, and you do the mopping and the cleaning and the spraying, and they like take one little toy and they put it in the basket. It's like, well, they helped, but they didn't. Your child is the double layer capacitor, right? That's what that is.
I feel like you're still harboring some like feelings from when your kids were 2 years old.
It's just an example. I don't know what you're
Just an
talking about.
example.
I just made that up out of nowhere. I don't even know what you're talking about. It's a total example at it with no.
There's a lot of details in that example.
I have no idea what you're talking about. I just made that up totally out of the top of my head. It's just it could happen to anybody.
It could happen to anybody.
Yeah. I don't know what you're talking. Okay.
All right, we got
Hey, real quick, move your chair. You're on a.
I'm on a thing. Yeah.
Hopefully the internet doesn't cut out. I just noticed it was on that. I didn't want us to lose internet.
We technically have 2 internet.
I know. I don't know which one it was, but I was just worried that all of a sudden, if the chair knocked it out, we'd lose internet. So anyway, sorry.
It looks like we're here.
We are here. I think we're good.
Like, oh god. Okay,
we're good.
Okay. All right. Next question. In CV, what could be a way to decrease the noise at low scan rates? Is there a math approach, or maybe in the POTStat setup? I use Excel to see the data after an experiment. Oh, so you can't even see it in real time.
I also like POTStat as an abbreviation of potential. You literally just took out NTO. Potentio. Like, are you?
Oh yeah.
At some point, are you saving time? Like, hey, I used my Potenstat.
Potenstat.
I saved time by not typing the I and the O. You know, it's not really an abbreviation at some point.
Oh yeah, what was it?
Just-
That reminds me of yeah, there's some abbreviations where it's like, oh, does this like you use this abbreviation because it's like less syllables.
Yeah.
But the sometimes the abbreviation is the same number of syllables as like the full word.
The word itself.
Was the word itself. I'm like,
Yeah.
you're not saving any more time.
No, you're not saving time at all. Anyway, I'm sorry, I didn't mean
But
to.
yeah, so there are ways you can decrease the noise at low scan rates. Like there are some physical setups. Number one, noise in CV at low scan rates often comes from things like what was it? Oh yeah, fair question.
There's only
Yeah, it's
150
characters.
characters.
Yep,
Okay,
yeah.
Fair enough. Maybe that I and that O, that was doing heavy
They're
lifting
doing
in
some
the
heavy
150
lifting.
character limit. So anyway.
So one thing, usually the noise in the CV at low scan rates is often due to convection. So that's just subtle vibrations. If you're going very, very, very slow, a sudden jolt or something will get picked up. But if it's scanning super fast, it's like, it barely had enough time to respond to it. So that's one thing, just keeping the system as vibrationally calm as possible. I've even heard of people, if you really have a lot of noise, some people even do experiments like at nighttime when like nothing's happening. Back when I was a graduate student, somebody was doing this etching process that was very sensitive. So they actually put vibrational like isolation dampeners, like to support the entire cell.
I've seen people use those. They look like a table with a bunch of holes in it, and it's like a,
like a laser table.
Yeah, and it absorbs vibrations or whatever.
Yeah, it's because it's like full of like nitrogen gas.
Yeah.
So it's literally floating. But basically, so there's that. You can put things in a Faraday cage to minimize like electrostatic noise, stuff of that nature. Also, there are usually some settings in the potentiostat where you can set like the stability filter. So sometimes, if, for example, a potentiostat's going to try to collect data often as quickly as possible, but if it's scanning very, very low, you're gonna literally pick up every single thing. But if you tell it to, only take a data point at a much slower scan rate, all that crazy noise and vibrations, they'll get removed because you're not scanning at, say, one data point per millisecond. You're collecting like one data point every 500 milliseconds. And so all the noise that's in the 200, 300, 400 millisecond, like that you would have collected during that time frame, that goes away. And you don't need that many data points because if you're going at like 1 millivolt per second or 10 millivolts per second, you don't need that kind of stuff. So that is the way to kind of decrease noise experimentally. Besides that, after you actually receive the data, there's just like filtering. You would need to do filtering algorithms,
or smoothing whatever,
stuff like that. So that's my take on it.
Yeah. Another way to put that, a last point you made is either it depends on your software you're using for your pot stat. Right. Sometimes they'll say it depends on what it looks like. It'll say like collect a point every 100 milliseconds or whatever, right? Or collect 1,000 points or 2,000 points, or collect a point every 1 millivolt, every 5 millivolt. Like, just recognize, however, if your potentiostat software has these settings, what it allows you to select for like a threshold, how often to take a point by time or by like millivolts or whatever, because that's what you want to decrease, to Alex's point, right? Take a point less frequently. Because again, if you're scanning 100 millivolts per second and you take a point every second, you're going to miss a lot. You're getting only 100 millivolt at a time. You're going to miss a ton. So the potentiostat at 100 millivolts per second is collecting points every millisecond or whatever, right? It's collecting points pretty fast. So you get all of the data. But if you're collecting a point every second and you're at like 0.1 millivolt, scan rate per second or whatever, you're getting like 10 points, whatever, you're getting 1 point per second. You're getting like a lot of data points in a very short potential window. So like you said, you're going to capture all of the little small changes and it's going to look noisy. So take a point less frequently is the idea.
Yeah. We have some questions. They almost sound like test prep questions or something like that.
They sure do.
But this first question: why does molar conductivity increase on dilution? And then it says parentheses reduction of interionic attractive forces. Maybe, but generally speaking, the molar conductivity does not increase when you dilute a solution.
Yeah.
So it's the other way around. So it's only under very specific conditions where something like that would happen. But if I have a 1 molar solution and it has a certain conductivity, if I dilute it to half a molar or 0.1 molar, the conductivity will decrease in like 99% of situations. They're only very limited. And then the question also becomes how highly concentrated, like is it a saturated solution? Is it a solid at that point? Where, yeah, you may have changes in molecular intermolecular forces. But yeah, for an electrochemical cell, that's generally not the case. And then the last kind of question here is if the measured EMF of the cell is 1.1 volt, calculate the pH of the solution. Well, that just by itself is not enough to determine the pH because you need to know more about like the chemical system, sort of say. If this was,
you use the Nernst equation, but you need to know what system it is.
Yeah, I mean, we don't know if that's a if it's the standard potential. I don't know like what side of the equation is like the H plus on or something like that. So yeah, you could do something. Yeah, the Nernst equation. If you knew what the reaction was and the concentration of the other species that are involved in the reaction, then you could start to do some of those calculations. But just that by itself, you can definitely have EMFs with a potential and then change the pH, and the EMF does not change because that's not what determines the potential of your system. So these questions are a little, they feel not complete.
Yeah.
Is what I'm saying. So Sunflower, if there's more information about these questions or if they're just given like that without any more context, I don't know if we'd be able to answer them. So
yeah, I think we'll have to leave that there because there's not enough information. And it does sound like it's just a lifted from a test prep of some kind. And so it's like, there's not much we can do about that, to be honest.
Yeah.
But Bilal has a good question. It says that for Mott-Schottky experiment, sometimes we get both positive and negative slopes in the same plot versus potential. How to know what potential range we should consider to decide a P-type or N-type material? This is a great question.
Yeah.
It just so happens that I recently did a webinar on Mott-Schottky, and I have a plot right here that just so happens to show you one such example. We have to move the question if it's in the way.
Yeah.
So you're probably referring to something like this, where you have your Mott-Schottky plot. So you have the 1/c² versus potential, and you have a positive slope and a negative slope. I was inviting this very question during my webinar, and nobody asked me. I showed this. I'm mildly insane. I obsess over my slides. I showed this graph on purpose during my webinar, if I can vent for half a second. And I showed this, and I talked about, hey, look, this is a negative slope. This is for a P-type semiconductor. And I showed this part, which has a positive slope, and nobody said, hey, why are there two different slopes there? And I didn't get a chance to answer it. And so thank you for at long last allowing me to talk about this problem. Okay. So in short, let me just annotate it for you so I'm clear. First of all, if I have a, if I have a negative slope, that is a P-type semiconductor. P-type. Okay. Why did I make that red? This line's green.
Well, the points are red,
I know, but
but the slope
oh,
is
that's stupid of me. I'm gonna write this over. Now it's bugging me
okay.
because I wanted to make it match. You know what I mean?
Yeah. Oh, yeah. Well,
All
no,
right.
I
So
hear you.
I'll make this a negative slope. Slope is p-type. So the simple way to remember this is it's backwards. On your Mott-Schottky plot, p positive, but the slope is negative. It's just how it works out, right? And then if I have a part where it's a negative, a positive slope, right? Positive slope. Well, you can guess what that means. It's an n-type. So positive slope is n-type. All right. So we've established that. So the first thing that I'll say to your question is if you have both, it can make it confusing. What is my type, right? Without having to get into all of the nitty gritty details, this is a whole webinar I did on this, right? For N and P type semiconductors, of course, they behave fundamentally differently, right? I'm zoomed in. An N type one has the Fermi level just below the conduction band. P-type semiconductor has the Fermi level just above the valence band. The way they bend is fundamentally different. So I know I, again, referred you to my webinar. I talk through this in great depth. I'll walk through this. So the short answer, again, to your question is you want to know as best you can beforehand what kind or type of semiconductor your material actually is. Now, I get it if you're sort of saying, I don't know, and that's what I'm trying to learn. But ideally, what you would have is some knowledge of whether your material is N or P type. It might be doped or something like that. And a lot of the times, if we have a material and we've manipulated it one way or another, we do have an idea about whether it's N or P type. Okay. Now, again, perhaps you don't for a variety of reasons. But basically, if I have to lower the Fermi level, which corresponds with an increase in potential. So if I have my flat band potential and which I get that you probably don't know what that is either, so fair enough. Basically, and if an increase in the potential going to positive potentials, okay, causes a slope like this. So if you could look at the green line, basically, to give you an example, the green line here. So if I started, for instance, at, I guess this is like minus 300, and I got a positive potential from there, and I have a Mott-Schottky behavior, which is to say that there's a straight line on my 1 over c squared versus potential. That's an indication of an N-type semiconductor. Okay, that's a band bending of this nature, and then vice versa. If I decrease the potential from the flat band, that's the other way. So I'm going from minus 300, I'm going down. I get a slope. That's a positive slope. That's, I think I said this backwards. Of course I said this backwards. It's just like my webinar saying everything backwards.
C1's greater than C2, C2's greater than C1.
I'm sorry.
It's okay. You good. You good.
Just I say everything backwards. Okay, hang on. So the potential goes up. Forget about what I said about the direction it goes. If you get a slope of these types, it's an indication of that type. Okay. Here's the tricky part for you. All right. There's a phenomenon that's called an inversion. And again, my webinar, I talk about the 4 different cases for N and P type. So this is an N type when I bend the bands properly, so to speak, I get a depletion layer. And then for a P type, when I bend the bands up, I get a depletion layer. There's the other instances where I bend the bands in the other direction, and you get what's called an accumulation layer. So sometimes what happens when you have a plot with both slopes is that you move the potential so far from the flat band that you get an inversion, or you go, I should say, in the other direction from the flat band, that you get an inversion where your majority carrier becomes your minority carrier and your minority carrier becomes your majority carrier. It's called an inversion. And this is what can happen. Okay. So the short answer is that if you just don't know anything about your material, you don't know whether it's supposed to be an N or a P type, and you don't know anything about where its flat band potential is supposed to be. Frankly, I have I don't know exactly what advice I would give you, because ideally you would know for sure, for instance, like this is definitely a p-type semiconductor. So this green slope here corresponds clearly with my proper band bending, and this n-type behavior is the inversion phenomenon, right? And so I can identify those and talk about those in that way. But if I just don't know anything about it, then how am I supposed to know whether my flat band is over here and this is the proper behavior, this is the inversion, or my flat band is over here and this is the proper behavior and this is the inversion? You know what I mean? You could go either direction. Like your flat band could be here at 0 and this could be a p-type semiconductor, or my flat band could be here at minus 500 and this is an n-type semiconductor. That's a tough place to be.
Did you talk about like adding a redox probe? Sorry, I'm like looking at other questions. I wasn't paying attention. Like, oh, he's got a whole webinar on it. He doesn't need any help from me.
But
he's got this. I can look at what these other people are saying.
I don't got this. So I'm trying to think about it through perhaps the way your question was worded, which it seems like you don't know if you have which type of material you have.
Oh yeah, as opposed to
and that's such a tricky thing to begin, because again, I'm explaining what the phenomenon is. I know it's difficult to kind of explain through, but this inversion kind of phenomenon, when the bands bend the other way, so to speak, you pop like an n-type, a p-type semiconductor does not have a lot of extra electrons at the surface. It has extra holes at the surface. But if you increase the potential a lot and you bend the bands down in the direction it doesn't like naturally want to bend, so to speak, you actually force extra electrons to the surface anyway. And you force the minority carrier, which is electrons, to be the majority carrier. And it behaves like an n-type semiconductor under those conditions. And so you'll get a positive slope in that case on your Mott-Schottky plot. But again, it's like in all of these cases, and I have a publication on it. Let me just share this with you. This is one publication. It's not something that I think like a lot of people maybe talk about all that much. I'm going to see if they have like maybe a plot on it, an inversion regime. Hang on. I'm going to see if I can find this paper that has, they talk about it. I'm not sure they have a lot of graphics, which isn't as helpful. Well, I'll share this paper anyway, because give credit where it's due, I suppose. But in this case, again, these authors are talking about in this inversion phenomenon that I'm talking about, where you'll basically get the other slope of your material. The reality is they know what kind of semiconductor it is, and so the inversion tells you, okay, well, I know it's an n-type, so it's behaving like a p-type under this inversion. So for you, again, I know I'm thinking out loud as I go here, but I can't think of a good example of how you would like know which side is the like correct one. You know what I mean? Which is the proper band bending, so to speak.
Well, so in your PowerPoint, maybe I'm wrong, but like you had like a flat region at what was it, positive potentials, where it's like, oh, it looks like there's like no change in like the capacitance or something.
That's correct.
Something like that. And then it moved, and then the capacitance just like went up.
So that suggests that the flat band is in that region, because the capacitance isn't changing with potential. Right?
Yeah, it's like you started in a region where like you're not getting very much stuff to happen, and then you go to much more negative potentials, right? And so in your picture, in your diagram, you had to go to like way negative potentials to such a degree that you quote inverted. You're just like pushing electrons into this, forcing electrons into the minority carrier situation. Is that, am I thinking about that right?
The tricky part is that the inversion comes even more negatively, and I would expect it to go in the other direction, right? So positive when you go to So in this case, for example, if this is a p-type semiconductor,
Yes.
then I'm going to
And you only get the positive slope for n-type only when you get a really negative
really negative
potentials,
potential. So
which is where you would expect it, because
that is right. That is
you're
right.
you're pushing all these electrons into the p-type. So
Yes.
you now have a weird behavior.
It's not the
So-
accumulate. It's yeah. So okay, let me try to explain this one more way, and then that we'll move on.
Yeah.
But I think you're right. I think I had
Maybe that's a way to think
rather
about it.
than, so the inversion is actually not the accumulation. It's actually a different phenomenon, but it's similar. So it's like what I have here. So let's say, like you said, this is probably
Yeah.
right here, like flat band, right?
Oh,
Region.
just,
I mean,
we'll just say for that. And you're at 0, you're a potential of 0.
right. Flat. This is roughly a flat band, right? In this region here, somewhere in here.
Sure.
So it's like I decrease my potential. So to this point here, decrease my potential, my Fermi level goes up, and I get this kind of band bending, this right here. So if I keep doing that and I keep bending the bands, eventually what will happen is that this tip is going to line up with the Fermi level, kind of, right? And that means that the probability of finding an electron in the conduction band increases.
Yeah.
And so it's going to start to have that inversion effect, because what happens is the Fermi level, let me, this line, I just want this line to be in front. So this line, if I keep bending the bands this way, I'm raising this higher, I'm decreasing the potential, I'm raising this higher and higher.
Yeah.
Eventually now the Fermi level is like here somewhere, which means that this is the 50-50 shot of finding an electron, which means that I now have a higher chance of finding an electron right here. That's in the valence band. And that's an inversion, because that's what an n-type semiconductor is. That's where the electrons are found in this band.
Yeah.
A p-type semiconductor would not normally have that. But by doing this, I'm providing enough energy now by bending it further for an electron to jump into the valence band. And now I have this inversion effect, which is where the minority carrier electrons
Yeah, the minority carrier
become the majority carrier. Or at
they
least
start
measurable
having that behavior.
Right. Okay, you've convinced me. That's the right way to think about
And
it.
you're at really low, like very negative potentials for that to happen.
That's
so
right. So
that's an explanation.
Okay, that's a great explanation. So, in summary, for you, Bilal, I think what you're looking for is hopefully you have a relatively flat region. If you don't, then I don't know what the hell to tell you. I'm sorry. But if you have a relatively flat region, and then you have an up and a down, or a down and an up, whatever it is, right?
Yeah, look at the potential where those things are
where
happening.
Those things are, yeah, right. And so probably the region, if you have any region, hopefully where the potentials are roughly constant or consistent, that would be an indication of the flat, near where the flat band should be. And so then you can figure out whether it's N or P type starting from there. And so, right, in effect, if that flat region is in the positive potentials, like I just showed, and you have to decrease the potential to get a negative slope, it's a p-type semiconductor. If it's the opposite, if your flat region is in the negative potentials, you have to increase the potential to get your positive slope. It's an n-type semiconductor.
Yeah.
So there you go.
I think that helps.
Thank you for getting me back on track. I was conflating the accumulation thing by the other with the inversion. The inversion is going further in the direction of the normal bending.
Yeah,
that's right. That's right.
Okay. Okay. So this is another looks like kind of a test question, but the person's in 8th grade. They mentioned, so I think we can at least talk about it. The standard electrode potential is an intensive property and does not depend on the stoichiometric coefficients of the half reaction, whereas Gibbs free energy change is an extensive property and does depend on stoichiometry. Using thermodynamic arguments, critically explain the statement. Also clarify why multiplying a half reaction by a factor does not change but does change, and how this is consistent with the relationship between them. And then this is saying, I'm in 8th grade and I have a number of doubts in electrochemistry. It becomes easy when we learn through animation. Fortunately, don't have any animations here. But
I don't think so, but I think it's as simple as pointing out delta G is NFE, the N in there.
Yeah.
The N is kind of the sticking point there. So delta G So I think the point here is delta G is affected by stoichiometry, and the potential is not.
Yeah, it's also weird because let's see. Well, in my opinion, it's like there's actually kind of a subtlety in the words. So in this part, there's a standard electrode potential, right? And the standard electrode potential is like the potential at STP under 1 mole of conditions. But we know that we could actually change the potential. Like you can get reactions to occur by changing, like you can get it to move by like 60 millivolts if you make it more of one versus another, changing the ratio of the half reactions. The Gibbs free energy is being described here as an extensive property that does depend on stoichiometry, which is to say that, oh, you can get more energy out of the system. But it's like, oh, but if you use the standard Gibbs free energy, the standard Gibbs free energy is an intensive property because it only refers to 1 mole of something.
Yeah.
Granted, I think that's relatively a minutia type of thing, because yeah, you can't get certain electrochemical reactions to occur at different potentials. It's like, no, they always occur at the same potential, but the amount of energy that you can get out of a system can change if you have more of it, right? So, for example, you can certainly get more energy out of a system. Now I guess the question is,
Well, if you think about this, but when you're talking about like, why doesn't the stoichiometry change the potential, right? Well, because like you said before, you definitionally said this earlier in our live stream.
Yeah.
The potential is like the amount of energy per coulomb.
Yeah.
That's the point, per coulomb.
Yeah.
So
that's right.
That is whatever is the I guess the term is
intensive,
is intensive. It already includes it's already like divided by the thing. Like it's so it's not a I don't know how to put it. I'm not,
and in Gibbs free energy, it's like joules per mole, but mole is mass. It's just the amount of a thing.
If you double the mass,
If you
or
double
the
the mass,
moles, then you get more energy.
Get more
out of
energy out of it. Yeah.
But the potential, it's per coulomb. So now I'm almost using the same argument. Now maybe that argument doesn't work. I'm trying to think of how to explain it properly.
You get more. Okay. Yeah. You're just saying, oh, if I just pumped in more coulombs, you would get more energy. You wouldn't get more voltage.
Right.
You'd get more current.
Yeah.
In the electrochemistry sense, because you'd get more molecules to flow, but if you will, the push, sort of say, is higher, sort of say. So, one way you can think about it is they are similar, because if I had 1 mole of something that had a high Gibbs free energy and I had 1 mole of something with a low Gibbs free energy, I'd get more energy per mole of the high energy thing. The energy per unit intensively it's an intensive property. It fundamentally depends on what the material is to figure out how much energy I can get out of it. So then it's like, oh well, but the potential is not. It's like there's a semantic argument. There's a fundamental like properties and materials argument, because if you do double the amount of the reaction that you do, the potential doesn't change, but the energy that you can get out does change. Because that's what engineers do like all the time. It's like, if you the voltage of your lithium battery doesn't change in series, but oh man, but you can get a lot more power out of it.
If I make a battery that's the size of my head and I compare it to a battery that's the size of my pinky finger, they have the same voltage, but one of them gives me more energy.
Yeah, one of them gives me more energy.
Right? It's the same amount of voltage because it's the same potential energy associated with them, but one of them has more material, so I get more current flow. I'm just trying to think of how to explain it.
How to explain it. That's
explaining it in This is good. It's a really good. It's a good question
Yeah.
because I've said this before, and it's like it's something I intuitively understand, but I don't know that I've ever found a good way to explain it.
Yeah.
Probably because I'm an engineer and I never think about explaining anything. I just say, hey, just multiply by 24 and it works or whatever.
24.5 and all the math
yeah,
works. So.
and raise it to some exponent.
Yeah.
Because it's like, yeah, that is a thing that I've taught before. It's like, no, you know, if I write the hydrogen evolution reaction as you know,
right.
2H plus 2 electrons gives you hydrogen, or H plus 1 electron gives me half hydrogen gas.
Yeah.
Same potential.
It's the same
It's
potential.
The same potential. It means zero. It's easy.
Yeah, it's zero.
But the point is the potential doesn't double or halve because you have the stoichiometry. It doesn't change. And maybe the simple answer is that the Gibbs free energy changes, but because E is NFE, if Gibbs doubles but N halves, or you know what I mean? Like,
like it's per electron.
It's already per mole of electron because the N is in the equation. That might be mathematically an answer. Again, it's not satisfying because it doesn't tell you like why, but it's a mathematical thing. You know what I mean?
Yeah. It's interesting because
I don't know if that helps at all or not. But.
Yeah, I know it does get into weird. Here's the other thing. It's like this is maybe like an 8th grade, like almost high school level, like question. And so the answer that the teacher might be looking for is like something super simple, and we're just like Ph.D.ing the crap out of it.
We might be going way too complicated.
We're going like way too complicated.
So one way else,
because everything you learn in high school is a lie.
That's correct. Delta G is minus NFE, right? This is forget about whether it's standard potential, regular potential, whatever. Just the relationship between Gibbs free energy and potential is here.
Yeah.
So in some ways, what you can say is if I have like A plus
E,
yeah, I was going to say sorry, I was going to do like 2E or whatever.
2E, yeah.
Let's just say 2 electrons, you know, whatever gives me B. Okay. I'm going to get some, you know, delta G here. Let's call this delta G1.
Yeah.
And then let's say I double this and I say 2A plus 4 electrons. I could write this which way I want, right? These are both correct. I might get a different delta G, right? Is that true?
Yeah. So the way. So
the point is the N changes, and so the E will be the same because
okay, yeah.
So I could say is that the E, if I just solve for E is equal to delta G, say minus delta G over NF, and F is a constant, right?
Yeah.
So the point is, if delta G, so this would be, let's just say this would be 2 delta G1. Right. Let's say this doubles. Yeah, I think that's what happens.
That's right.
Right.
Yeah.
So you say, well, what is the potential? Well, the potential is the same, right? For both, it's the same. It's E, because if I have E is equal to minus delta G over NF, but now I doubled my delta G. Well, I also doubled my N. Because I went from 2 to 4 or 1 to 2, whatever.
Yeah.
So the 2 goes away. And so the potential is the same anyway. So in other words, the stoichiometry changes the delta G, but it does not change the E because of this definitionally.
Yeah.
So that might be a quick way mathematically to explain it. Now, again, the reason I don't like that so much is because it's just math. And if you're wondering why chemically, fundamentally, right? First principles, which is what we're doing as a PhD. And you might not care about that as an 8th grader, maybe, or maybe you do. And maybe you're very, interested in this kind of higher level thinking or whatever, which is great. It's harder to explain, but that's mathematically how you might conceptualize it. So maybe that's helpful. Anyway.
Yeah. And hopefully that kind of answers it. Good. Just kind of,
exactly. E remains
constant. And changes. E remains constant.
Exactly.
Okay. Good. All right. That helps. All right. I think we have time maybe to answer
a few more questions. This first one another one about Mott-Schottky, but I'm not sure I can exactly answer.
Yeah, I think we also I think I want to say this was like a comment in the fact that like, oh, every time you do Mott-Schottky, it gets like a different value. And so
Mott-Schottky with carbon nitride doing Mott-Schottky. The plot changes every time, even with the same substrate.
I think there's experimental things, and also if you're not putting the redox
Carbon
species
nitrogen.
in, something is maybe different, between each one. Also, are you removing your native oxide layer? I know these things are always hard working with HF and kind of random stuff like that.
So it
Yeah.
is a semiconductor, 2.7 EV. Okay. I don't know a lot about carbon nitride specifically.
Yeah.
Nitride, if it's nitrogen, it's probably a p-type semiconductor. No, it's an n-type semiconductor, excuse me. Yeah, nitrogen has what, 5 valence electrodes, so it's going to be a n-type semiconductor. Like I don't know how much more I can exactly answer. It's the plot's changing. This is just experimental consistency. Like there's a lot to work on, and semiconductor electrochemistry is just fundamentally difficult too. If you're trying to do Mott-Schottky, ideally I think you don't want to have a Faraday, try to not have a redox active species that might, mess with your with the potential of the electrode. You don't usually, or maybe you do want to nail it down by having a redox couple. Like there's stuff like that. Like try tinkering with the electrolyte, maybe. Try making sure that your substrate and everything is well constructed. A lot of times this is just practice. There's a lot obviously of practice that requires it, but it's hard to give any more advice without seeing your data or knowing more about your system, precisely. But all I can say is, right, electrochemistry it's hard, and it just requires trial and error and practice. I don't know what else to say. Yeah, good luck, I guess.
Yeah.
Maybe this will be the last question here, I guess. It's
sure.
Some questions about solid oxide.
Solid oxide
electrolyte. What is that? Solid oxide electro. I'm not sure.
Electrolyte.
EIS of solid. It seems like solid oxide fuel cell. Maybe it's just a typo.
Yeah.
Fuel cell.
Yeah.
Noisy and low frequency. This I'm noticing in high steam, 50%. Do I have to do something with the gold wires, like twisting? No, that's not gonna help. Twisting is gonna help. Twisting your wires will help if you have noise at high frequency most of the time, because twisting the wires can help reduce inductive effects. If you're having noise and low frequency, it's probably not inductive effects. And even so, twisting the wires isn't likely going to matter, I think.
Yeah.
So I wouldn't expect that to be an issue. The follow-up here is for a high temp SOEC. What is SOEC? I just want to.
Yeah.
Oh, electrolyzer, not a. So it's just the opposite. I was like, it was ringing a bell. I couldn't put it together. Okay, so for a high temp electrolyzer, my leads are very long due to the furnace size. How can I maintain a stable twisted pair at 800C to stop noise without the wires untwisting or shorting? Well, again, I don't know that you need to twist your wires necessarily unless you have high frequency inductive noise.
Yeah.
But the long wires can cause added impedance for sure. Not necessarily inductance per se, but for sure you can be adding extra impedance. How can you stop noise? So first of all, noise at low frequency is pretty common. It's pretty normal. I know it's not ideal, but I don't know that there is a lot you can do practically, especially with high temperature fuel cells and electrolyzers. You're usually between 500 and 800 or even 1000 C. That level of temperature requires long leads you can't put your potentiostat at 800 C. It's going to die. So I'm trying to think, like, how could you even I've seen a lot of data from solid oxide, like high temperature fuel cells, and a lot of times it just is noisy. Like you'll deal with noise at these low frequencies and stuff, and you have gas flow, and you're dealing with a lot of stuff. I mean, you just the simple, maybe not satisfying answer is like to really just make sure that the leads are solid and well connected, before you heat it up. Don't scald yourself, I guess.
Yeah.
make sure that they're properly connected before you get it at temperature. Make sure that nothing's high temperature causes degradation of a lot of materials. So make sure that anything you have holding it all together is nice, is stable and solid, I guess, right? I mean, you could try twisting the wires. I just don't think that's going to make any difference, especially for low frequency. I don't think that's really the problem. Honestly, I have a hard time thinking of other, again, it's another one of these things that perhaps if I saw your setup, I might have some suggestions, but like low frequency noise is pretty common, and high temperature fuel cells and electrolyzers are just sort of fundamentally difficult to work with.
Saying ceramic insulated wire twisted or coax in a grounded tube. Look at high temperature thermocouple construction. That's a good recommendation.
Yeah. So this is more to the point that I'm just like, make sure your connections are solid. You might have to use something different, some coax tube or something else. Use a different insulation wire. I don't know. Because that's the other part that's difficult to know is is the noise at low frequency because of the connection, or because that's just what is happening at low frequency. You have some like diffusional effects that usually slow high impedance kinds of processes cause noise at low frequencies, right? And so you're at a fundamentally difficult question to answer, which is that, is my noise a result of my setup, my system, or both? Right. And so, yeah, I don't know. Again, temperature compensate the junction. That's another good point. So at high temperatures, you can get, I don't know, voltage drops across junctions and things of that nature. So I haven't personally done SOFCs and things like that. I know a little about them. I mean, I've studied fuel cells and stuff, but the practicality of doing really high temperature fuel cells is not something I have personal experience with. So yeah, there's probably a lot of little things that you need to know about. You'll end up compensating for, or building your setup to accommodate. And again, it's another one of these things. It's going to require some trial and error probably. But I'm not sure I can say too much more about it, unfortunately.
Yeah. Sorry. Yeah, I don't know anything about it.
Yeah.
To help.
Well, we'll leave it there.
Yeah.
For now.
Yeah. Sorry if we couldn't get to any other questions. Do tune in next week. I think we're both here next
yeah, I think so.
Yes.
I think we should be here. So
yeah,
join us next week. As we mentioned, go to our website, pineresearch.com, pineresearch.com/contact. And if you want a question answered in the middle of the week and you think of something, and send us a contact and an email and everything, and we'll be able to answer that question. We'll give priority for the first part of our webinar. Here I am misidentifying our thing. It's a live stream. Good. Yeah. In any case, give us a contact on our website if you want to ask a question. We'll give priority to that. And otherwise, I guess everybody have a great weekend, a great rest of your day, and we'll see everybody next week.
Bye.
Bye.